Picture a multi-million-dollar data center, right? The kind powering the next generation of artificial intelligence.
Right.
Or maybe think about that brand new, super high-performance electric vehicle you're maybe thinking about putting in your garage.
Yeah, exactly.
We tend to view these things as, these incredibly sleek, flawless end products. But to get to that polished state, there is this distinctly brutal, totally unglamorous process happening behind the scenes.
Oh, absolutely. It's intense.
Right. So think of these high-stakes technologies as the most exclusive tech clubs in the world. If a faulty microchip somehow manages to get past the velvet rope and inside that club,
It's a disaster.
yeah, the results are catastrophic. We're talking cascading system crashes, battery failures, just total chaos. You need a bouncer at the door.
A very strict bouncer.
Exactly. A ruthless, highly specialized bouncer whose entire job is to ensure that only the absolute most resilient, flawless chips make it inside.
And today, we are actually looking at the operational and, well, the financial X-ray of the company acting as that exact bouncer.
Yeah, we are.
We're doing a deep dive into Aehr Test Systems, specifically their fiscal 2026 fourth quarter and full-year financial results,
Right.
which were just released on July 14th, 2026.
Fresh data.
Very fresh. And this document, it's far more than just a balance sheet for a tech company out in Fremont, California. When you decode how this specific testing company is performing, you're essentially reading a diagnostic map.
Right.
A map of where the biggest tech giants on the planet are desperately deploying their capital just to avoid catastrophic manufacturing failures.
Which is huge because the stakes are incredibly high right now. And that's why we really need to start by decoding these financials.
For sure.
Because the trajectory revealed in this document, it really sets up the massive physical scale of everything we're about to discuss today. Let's look at their fiscal fourth quarter for 2026.
Okay, let's do it.
Net revenue hit $18.8 million, which is up from $14.1 million in the same quarter the year prior.
A solid jump.
Yeah, and they also flipped a previous Q4 net loss into a GAAP net income of $1.4 million. And just to be clear for you listening, GAAP stands for Generally Accepted Accounting Principles.
Right, so it's the real deal.
Exactly. It means this isn't some, fuzzy adjusted tech industry math. This is a standardized audited profit. But the real shocker to me is their cash position.
Oh, the cash leap is wild.
Total cash and cash equivalents rocketed from $37.1 million at the end of February to $116.5 million by late May.
Yeah, and if you dig into the consolidated statements of cash flows, you can actually see the mechanics of how they built that fortress.
Mm-hmm.
They brought in over $97 million in proceeds from issuing common stock through public offerings. So they went to the market, raised a massive war chest, and are now sitting on a highly fortified balance sheet.
Ready to deploy it.
Exactly. They are positioning themselves for a massive scaling operation.
Okay, but I have to challenge this narrative of total victory for a second.
Okay, hit me.
Because I caught a pretty glaring contradiction in these numbers. We just talked about a great fourth quarter, sure. But if you zoom out and look at the full fiscal year for 2026,
Oh, yeah.
their total net revenue was $50 million. But in fiscal 2025, that full year number was $59 million.
Right.
So their year-over-year revenue actually shrank. And they also posted a GAAP net loss for the year of $7.1 million, which is, well, it's significantly worse than the $3.9 million loss from the year before.
It is.
So why on earth is the industry treating this earnings report as a massive win if their full year revenue actually went backward?
It's the exact right question to ask. You see a shrinking annual revenue and a widening loss.
Yeah.
And the instinct is just to assume, hey, the company is struggling.
Right.
But what's fascinating here is that the market isn't looking at last year's $50 million.
Mm.
In hardware and heavy manufacturing, past revenue is basically a rear-view mirror. The entire industry is focused on the windshield, which is the backlog. If you look at just the fourth quarter, Aehr booked a record $60.7 million in new orders.
Wow.
Yeah. They secured more guaranteed future work in 3 months than they delivered in the entire previous 12.
That's insane.
It is. As of May 29, their official backlog was $80.6 million, but they cite an effective backlog of $100.6 million when you include the concrete bookings that came in right after the quarter closed.
Okay, let's unpack this. An effective backlog of over $100 million for a company that just delivered $50 million in a whole year.
Right.
That means they have twice their annual revenue already sitting on the desk waiting to be billed.
Precisely. And in the equipment manufacturing space, A backlog that size gives a company a level of visibility that is incredibly rare.
It's guaranteed money, essentially.
Guaranteed demand. And it's what allows their CEO, Gain Erickson, to make an incredibly bold projection in this document. He states that for fiscal 2027, their revenue is projected to be between $130 million and $150 million.
Wait, projecting up to $150 million next year after doing $50 million this year?
Yep.
I mean, that's 160 to 200% growth rate in a single 12-month period.
Yeah, and you don't project 200% growth in heavy industrial testing equipment unless you are riding an absolute tsunami of physical demand.
Makes sense.
And the report spells out exactly what is generating that tsunami. It's the global race to build out artificial intelligence infrastructure.
Okay, that transitions us perfectly into the actual technology here, the stress tests themselves. The report links heavily on a massive shift toward wafer-level burn-in, or WLBI.
Yes, WLBI.
Ericsson notes that their lead AI production customer is shifting their burn-in testing away from system level to all wafer level for their AI accelerators. Let's put this shift into perspective for a second. When we say burn-in, we are talking about physically running high-voltage electricity through a chip at extreme temperatures.
Literally trying to cook it.
Right. You are trying to force it to fail if it has even a microscopic defect. You want it to die right there on the factory floor, not 6 months later in a massive data center.
Exactly.
So is this shift to wafer-level testing basically like an automaker realizing it is infinitely cheaper to crash test the engine blocks individually while they are still on the assembly line?
Oh, that's a great way to put it.
Rather than, waiting until you've built the entire luxury car, polished the paint, and then driving the whole finished vehicle into a brick wall?
You are hitting on the core of the yield problem.
Mm-hmm.
Think about how a microchip is actually made. You start with a semiconductor wafer, which is a large, flat, delicate disk of silicon.
Okay.
Printed on that single disk are hundreds, sometimes thousands, of individual chips.
Right.
Eventually, that disk gets sliced up, and the healthy chips are packaged into a final system surrounded by heat sinks, memory modules, and expensive substrates. All the expensive extra parts. Right. And historically, a lot of this heavy stress testing happened at that final system level.
Mm-hmm.
But if a chip fails at that late stage, you haven't just lost the silicon.
You've lost everything.
You've lost the expensive packaging, the labor, and all the other perfectly good components it was permanently attached to.
So you've literally totaled the luxury car just to find out a single spark plug was defective.
Exactly. By moving the burn-in process to the wafer level, you are testing all those thousands of chips simultaneously while they're still on the uncut silicon disk.
Wow, all at once.
But mechanically, this is an incredibly complex physical feat. You have to perfectly align microscopic pins to touch microscopic pads on thousands of chips at the exact same time.
That sounds impossible.
It's extremely difficult. You pump intense electricity through them, and most importantly, you manage the massive amount of heat they generate.
Right, so they don't just melt.
So they don't just melt into slag, yeah.
Yeah.
By identifying the weak links before you spend the money packaging them, you drastically reduce yield loss.
Which is huge for AI.
It is. For AI accelerators, which are some of the most complex and expensive items ever manufactured by humans, catching failures at the wafer level saves millions of dollars per production run.
And Aehr's technology seems to be the gold standard for pulling off that physical feat. I mean, the source details a massive benchmark win.
Oh yeah, a very big deal.
Aehr successfully tested a top-tier AI accelerator and CPU supplier's processor, exceeded their expectations, and is now moving to pilot production for a current high-volume device.
Right.
They are even evaluating a second device in parallel. This is a major, unnamed AI titan deciding that Aehr is basically the only bouncer they trust to guard the door.
And, the challenge of heat and power doesn't just stop at the wafer. We also have to look at package-level testing,
Right.
which Aehr addresses with their Sonoma systems. The report highlights record follow-on production orders from their lead hyperscale customer. Now, hyperscalers are the companies building the massive warehouse-scale data centers,
The physical backbone of the cloud.
the physical brains of the internet, pouring billions into this stuff. And this specific hyperscaler is forecasting a huge expansion of purchases for a second device.
Oh, why a second one?
Because this new AI processor requires twice the power per package as the first generation.
Twice the power, which physically means twice the heat twice the thermal stress,
Right. Gotcha.
and twice the risk of catastrophic failure if it isn't tested correctly.
Right. As AI language models grow larger, the computation requires just unprecedented amounts of electricity. The thermal dynamics happening on these chips are extreme.
It's wild to think about.
It is. Managing that heat during a stress test requires advanced liquid cooling and really precise thermal control.
Yeah.
Testing them to guarantee reliability under those extreme real-world data center conditions is a critical bottleneck for the entire AI industry.
And Aehr has positioned its equipment as the solution to that bottleneck.
Exactly.
So we have these incredibly hot, powerful AI processors doing the heavy thinking, but a single AI chip can't train a massive language model on its own.
No, not even close.
You need thousands of them working together, perfectly synchronized in a server farm, which means they have to talk to each other fast.
Very fast.
The processors are only as good as the networks connecting them, which brings us to the next massive growth area in a report, silicon photonics.
Yes. If we connect this to the bigger picture, the architecture of the modern data center is hitting a hard physical wall with traditional copper wiring.
Okay, how so?
For decades, we've moved data by sending electrical impulses over copper. But when you try to push the massive amounts of data required by AI across copper wires at incredibly high speeds, the physics turn against you.
It gets hot, right? You run into physical resistance.
Extreme heat, severe signal degradation, and honestly, it consumes a massive amount of power just to push the signal a few meters.
So what's the fix?
The industry solution is silicon photonics. Instead of using electrons traveling over copper, you use photons, light.
Light traveling over fiber optics.
Right.
We are talking about literal microscopic lasers built directly into the silicon chips, moving data at the speed of light.
Optical input and output, or optical I/O. It is exponentially faster, generates far less heat in transit, and completely slashes power consumption.
Sounds like magic.
It does, but manufacturing microscopic lasers and optical sensors on a silicon chip is a highly delicate process. A laser is incredibly sensitive to temperature fluctuations and structural imperfections.
Which raises a huge mechanical question for me. If you are dealing with literal light lasers and microscopic fiber optic alignments on a chip, how do you physically stress test that compared to traditional electronics?
It's tough.
I mean, checking if an electrical circuit connects is one thing, but testing a laser sounds like a total quality control nightmare.
Oh, it is exponentially more difficult. You aren't just testing whether electricity flows. You are testing optical alignment. You have to verify the laser output power.
Wow.
You have to ensure the wavelength of the light doesn't drift when the chip heats up to 100 degrees Celsius. You have to burn in these photonics devices for hours or even days to guarantee the lasers won't degrade over years of continuous data center use.
And looking at the earnings report, the demand for this highly complex testing is just surging. Aehr notes that their lead silicon photonics customer is actively ramping up with fully automated wafer-level burn-in systems.
Yeah, but there's an even bigger detail in there.
The new customer.
Exactly. The detail that really stands out is a brand new customer. A global leader in networking products is forecasting additional systems this calendar year, specifically to support next-generation hyperscale data center deployments.
That feels like a huge market signal.
It is a critical market signal. When the global leaders in data center networking start buying millions of dollars of burn-in equipment to test their next-gen optical equipment, it confirms that silicon photonics is no longer an experimental, futuristic concept.
It's here.
It is the immediate physical reality required to scale AI infrastructure. Without these microscopic lasers, the AI data centers basically choke on their own data traffic. And once again, Aehr is sitting right at the toll booth.
It really shifts your perspective. Just thinking about the vast, hyper-cooled physical infrastructure required, the literal lasers firing across warehouses just so you can, ask an AI chatbot to write an email for you.
It's wild.
It really is. But data centers aren't the only sector grappling with massive power loads and extreme heat. That brings us to another major pillar driving Aehr's massive backlog, and it's out on the physical roads.
Yeah.
The report outlines an aggressive rebound in testing for electric vehicles, specifically revolving around silicon carbide.
Yeah, the report points to highly encouraging signs of recovery in the power semiconductor market. Specifically, silicon carbide, often abbreviated as SiC, and gallium nitride, or GaN.
Okay.
These are the specialized components driving automotive electrification.
So what does this all mean if you're, let's say, thinking about buying an electric vehicle in the next few years? Why is the auto industry pivoting to these specific materials?
Well, traditional silicon chips are phenomenal for processing data, but they have physical limitations when you ask them to handle massive voltages and extreme temperatures.
Okay.
If you want an electric vehicle that can charge from 10% to 80% in 15 minutes and efficiently squeeze every possible mile of range out of a heavy battery pack, you need to transition the vehicle's architecture to higher voltages.
Like 800 volts or more, right?
Often 800 volts or more. Traditional silicon struggles there.
Yep.
But silicon carbide is what's called a wide bandgap semiconductor.
Meaning it can physically handle a much higher electrical field before it breaks down.
Exactly. It thrives in high-voltage, high-heat environments.
Mm.
It allows the power components in the car to be smaller, lighter, and vastly more efficient at converting battery power into mechanical torque.
And gallium nitride.
GaN operates on a similar principle, but is particularly exceptional at high-frequency switching, making it incredibly useful for the vehicle's onboard charging systems and power adapters.
But just like the photonics we talked about earlier, these are newer, complex materials. And they are notoriously difficult to manufacture without microscopic defects.
Right. And the stakes of a defect are entirely different here.
How so?
In a data center, a chip failure might mean a slight delay in processing a web request. In an electric vehicle traveling 70 miles an hour down the highway, a failure in a silicon carbide inverter means the entire powertrain could instantly shut down.
Oh, wow. Yeah, that's bad.
The reliability requirements are absolute. There is zero margin for error.
Which totally explains the absolute paranoia you can read in the actual orders Aehr is fielding. There is a specific detail in the report that is fascinating. In just the last month alone, Aehr received $8 million in new orders for their wafer packs.
Yeah.
And just to clarify, a wafer pack is Aehr's proprietary contactor. It's essentially an incredibly complex, custom-built circuit board cartridge that perfectly aligns thousands of microscopic probes with the silicon wafer, acting as the physical bridge to push the extreme electricity and heat into the chips.
Beautifully described.
Thanks. But listen to who actually bought them. The report states that this key order came directly from one of the largest automotive companies in the world.
Not a supplier.
Right. The automaker bought the wafer packs directly to qualify the silicon carbide devices from their suppliers for a new generation of EVs.
In the automotive supply chain, that is highly unusual and incredibly telling. Normally, a massive automaker buys the finished, tested component from a Tier 1 supplier and trusts that supplier to handle their own quality control.
Right.
For one of the largest automakers on the planet to bypass that norm and directly purchase the stress testing equipment from Aehr, well, it reveals a massive shift in supply chain dynamics.
It tells us they fundamentally do not trust the suppliers to do the testing right on their own.
They don't. The automaker is mandating a specific, rigorous standard of testing using Aehr's FOX wafer-level burn-in systems. It shows how utterly critical silicon carbide reliability is to the safety and viability of their next-generation vehicle platforms.
It's life or death for the brand.
Yes. A massive recall due to a premature power chip failure could cost billions of dollars and severely damage a brand's reputation. So, the automaker is taking authoritative control of the quality assurance process by mandating Aehr's exact testing technology across their supply chain.
It comes right back to the bouncer analogy. The automaker is standing at the door of their own assembly plant, holding Aehr's wafer pack contactors, telling their suppliers, nobody gets into this vehicle unless you pass this exact stress test. And Aehr clearly sees this demand broadening because the report also expects renewed demand driven not just by electric vehicles, but by the power infrastructure needed for AI data centers.
Oh, absolutely.
Because those massive server farms. They also rely on silicon carbide and gallium nitride chips just to manage and regulate the unprecedented amounts of electricity flowing from the power grid into the processors.
It represents a really beautiful convergence of Aehr's core competencies, whether it's stressing the AI processor, doing the deep learning, the microscopic laser transmitting the data, or the heavy-duty power chip regulating the electricity for the entire facility. Aehr has positioned its wafer-level and package-level burn-in systems as the mandatory physical checkpoint for reliability.
Which perfectly brings us to why this dense, deeply technical financial document actually matters to your everyday life. Chances are you will never log onto a website and buy an Aehr Test Systems FOX wafer pack contactor.
Highly unlikely.
It is a highly specialized, purely industrial piece of hardware, yet modern life is rapidly becoming entirely dependent on them. The reliability of the generative AI tools you are using at work, the speed of the fiber optic networks that run the global economy, and the literal physical safety of the high voltage battery in the electric vehicle you drive your family in.
All connected.
All of it relies fundamentally on the extreme physical stress tests the single company in California is performing. They are the unseen quality control layer of both our digital and physical future. They are the bouncer keeping the disasters out of the club.
It is a profound level of responsibility for one company to shoulder.
Yeah.
And as we synthesize all this, it raises a lingering question, something to mull over after we wrap up.
Yeah.
If an obscure behind-the-scenes testing company is projecting up to 200% revenue growth in a single year, exclusively to keep up with the physical quality control of new AI processors and EV power chips,
Right.
what does that tell us about the staggering physical scale of the infrastructure currently being constructed around us? We talk about the cloud and the AI revolution as if they are these ethereal software concepts.
Miserable.
But looking at the sheer volume of high-voltage testing equipment being purchased, are we vastly underestimating the massive physical footprint, the intense thermal dynamics, and the staggering energy requirements of this new era of technology?
It's an incredible question to leave on. The cloud isn't just invisible code in the air. It's incredibly hot, incredibly powerful silicon that draws massive amounts of electricity. And every single millimeter of it has to be brutally tested before it gets turned on. Thanks for joining us on this deep dive. We'll catch you on the next one.